substance Z has a heat of vaporization of 494.2 joules.
Okay, so delta vape 492 joules.
494.2 joules per gram.
Okay.
And has a specific heat of 2.835.
Okay, so specific heat is equal to
2.835 joules
per gram Celsius.
Yeah, Kelvin.
Oh, grams Kelvin. Well, it'll be the same thing.
Yeah, because it's just a change in temperature.
It's just a shift.
And a boiling point of 296.4 Kelvin. How much total energy in kilojoules would be required to raise 12.17 grams of liquid sample?
12.17 grams.
Yes.
Okay.
Liquid to the boiling point, and to completely boil the liquid, if the initial temperature of the sample is 269.3 Kelvin.
Okay.
So it's similar to the
269.3
Kelvin. So it's similar to the other one in the fact that, well, let's see, it just says boil it all off, so that'll all occur at one temperature. Wait. How much total energy in kilojoules?
Oh, okay. I see what we need to do. Okay. So we need to first figure out, so the heat of the actual vaporization is simply going to be this guy times that. Okay? So that's going to be the heat just for the transition.
It's similar to this, because you're just converting, and then when you multiply by that, you get joules. Okay.
Yeah. So we get a joule amount there. And then for the heat of, for the actual heating up to get to that point, we're going to have to do the difference between these two temperatures, and then we're going to have to use this to solve for J right there. Okay, because we know that the energy is equal, or energy over the mass times degree, or times Kelvin, I should say, is going to equal C. But because we got C and we want to solve for M, then we just got to simply take this and we're going to multiply it by the mass times the Kelvin to get just E by itself, the energy. And then we take the sum of that energy and the sum of the energy that we get right there.
I've never seen it before.
I just made it up.
Oh, that? Okay.
I just shifted the equation, and I'm probably using different values.
What is, so C, I'm sorry, C is?
So C is the heat capacity. This guy.
Okay.
Okay. I don't know what symbol they use for C. I've used C for the heat capacity.
Right, and then K, could it be delta T?
Yeah.
Okay, that's what it is.
K is going to be delta T.
I know what you're talking about now.
Okay, so let's figure out delta T first. So we've got 296.4, 269.3. We subtract, we get 172. You get 27.1. Awesome. I can still do subtraction without a calculator. Okay, so 27.1. We're going to go ahead and we're going to plug that into our equation. So E is equal to our heat capacity, which is 2.835 joules per gram per Kelvin. And then we're going to multiply that times our mass, which is 12.17 grams. So because we have grams on top and grams on the bottom, that's going to cancel out. And then we're going to multiply that by our change in temperature, which is 27.1, and then Kelvin, leaving us with just joules.
get 935.
935.
00.
Okay, 0.0 joules. Okay, so we're gonna, that's one of our parts. Now let's go ahead and figure out the other part. So we just gotta multiply the mass. So 12.17 grams times our heat of vaporization, yeah. So it's gonna be times 494.2 joules per gram. And that's gonna equal
6,014.4.
6,014.
6014.4. Yeah.
And that's joules. And then we just do the sum of both, so 935.0 joules plus, we get 4, we get 9, we get 4, we get 9, we get 6. So approximately about 6.9 kilojoules, or 6,949 joules. There we go.
Okay.
Makes a little bit more sense now?
Yeah, I don't know how you did. How do you not remember this stuff, but you get it?
I've done stuff like this in 106, but slightly different.
Okay.
But the principle is, it's universal.
So,
And it's just math. Math is fun.
initial temperature of the sample. So you just did change in temperature from the boiling point to the initial temperature,
Mm-hmm.
which is what we need to find. And you found the energy associated with this sample. We have to use this specific heat. What is? How much total energy would be required? So basically, what you found was vaporization. Okay, so you found the energy required to vaporize the whole substance.
Yep.
And then what is this energy for? The 935?
The 935?
Yeah, what was that?
Oh, so this energy right there, that was the energy required to raise the temperature. And then the 6,000 was energy required to do that transition from liquid to liquid to gas.
So if we were going in order, then you would do the 935 would come first because you raise the temperature to boiling, and then the vaporization goes because it turns into gas. Okay.
Yep.
I'm gonna write that down.
Go ahead.
Okay.
Yep, this is a really good review.
Is there a lot of stuff on there? Or do you probably remember it?
No, this is the first time I've seen this semester. So, because it's barely coming up. I've seen similar things, but with different. Actually, I've seen it just for change in temperature, not the actual vaporization or the actual melting.
Mm-hmm.
But I've seen it just for the change in temperature. So that part I'm familiar with. Mm-hmm. Yep, make sure to label it a whole lot better than mine. Well, let's see, so this is
So you know it's definitely.
this is a mass.
One thing I do find helpful is, but I rarely do it because I'm so lazy. But like, label the whatever it is, so joules, or give it the whole.
Yeah.
Just
So-
like you said, you can kind of figure it out based on what the final answer. So if it asks for joule or joules over grams, then you know you have to divide by. Yeah, so I think that's helpful. How many significant figures would we have in this problem?
Well, it looks like we'd have 4 because we got 4 there, 4 there, 4 there. We've been using 4 there. This one has 4. Yeah, they do it really easy for you.
What about, so how is, so on that one, delta H, what are we finding?
So this one should be 6.949.
Yeah. But I wonder, so the change in temperature is 27.1 Kelvin. Is that, you have more, no, you don't. Yeah, that's where I'm confused, so.
How we went from 3 sig figs.
We went from 4, I guess, right?
Yeah, we went from 4 to 3.
And you do it based on,
Well, we do it based on the original data that they give us.
so this one has, because I thought we said, I can't remember if we said, when you subtract, you keep it significant to the decimal place and not the,
Yeah.
is that right?
So the decimal place has to remain the same. So there we had 1 in each decimal spot. So for sure we would only have 1. If it was a 2 and a 1, we'd just go with 1.
So this one actually has 27.1 has 4 significant figures in it because it's based on wait, it has unlimited in a sense because if you multiply this by like a million, then and the million was all significant digits, then it would be an all out 0.1.
Yeah.
Okay, thus there's 4.